Right. Okay. Just give me a second to make sure that this camera is going to switch on. Does it want to switch on? No, it quit. Let's just ignore and reopen. Oh, come on. P2V. Pretty sure. Oh, there we go. That's excellent. Okay, good. I'm going to use this today. And the other lecturers don't like it, but I love this little camera. Except that there's a funny shadow, but that's fine. We'll survive. Yes. Ooh, the green U on screen. Where is that coming from? Nowhere. Okay. And let's just see what it says here. And we should start. We're live on air. We're broadcasting on YouTube. That's fine. Right. So today we have to talk about data representation. I'm sure. Okay, now. Oh, so many things to remember. First off, let's see if I can find her. But she's moved. Where is Danielle this morning? Oh, right here she is. Danielle, just stand up, and Benny wearing the same clothes as in his student photo. Is that the only top? I just happen to know. So are you wearing the same clothes as in your student photos on your student cards? That's excellent. Okay, so this is Danielle and Benny, the class representatives. If you have an issue, please send them an email. And how do you know their email addresses? Well, I promise that by Monday the website will be up. Over the weekend, I'm going to start putting up. I'll start putting up some of the. Oh, I didn't have to actually even have them set up, but it's good to know that they're live and that they're good. That's fine. I guess, but over the weekend, today I'll start putting up parts of this website, and by Monday will be all live. There are the email addresses, and I guess that's your official email address or not? Do you use that? Do you have another email address? I'll find it on the system. And Benny, use this. Okay, I'll find yours on the system and replace it. You don't have to check in 2 places. It's really important that if you do have an email address, make it your only one. Unless you want to separate university and private life, who wants to do that? Okay. So if you have issues, please contact them. If you have complaints, I can take it. I don't mind. Please speak your mind. And once the forum is up and running, I hope that you'll be using it and complaining on there as well. Now, one more important thing, and that is, if you went to the site yesterday, you could not log in, and you did not fix it with Paul, our system admin, or you did not write your name on a piece of paper. Please come to me afterwards, because we must set up your login. There won't necessarily be an opportunity to do that in the next tutorial. Paul may not be there, and then you have to sit through the whole tutorial doing nothing. Here is Dirk. Well, I haven't put in the description for Dirk. This is not a dot. But this is Dirk Brandt. He's our head teaching assistant. And in fact, you won't see me in the tutorials in the future. Dirk will be handling all of that. So Dirk is like a second to you. You must obey him. Okay. Good. So that's, let's see, that is the people. Now we have to talk about data representation, which is what today should be about. I'm an extremely slow lecturer. Last year, there were only 2 lectures a week, and the 3rd lecture was something else, invited talks. And the lecturer told me that there's not enough material to cover in the course, but I think there's too much material. I go slow. I'm sorry about that, and you must tell me if I should speed up. But let's see if we can get through at least data representation. This stuff is extremely important because in the computer, we need to. It's vital to know how data is stored in the computer. You'll be using this year, next year, in your 3rd year, in honors, when you do your masters, when you're doing your PhD. What's your name? Stan. Stan. Oh, I'll just call you Stan. Stan, when you're doing your PhD, you'll still be using data representation. The computer does not store files the way we want them to be stored. It stores zeros and ones, only zeros and ones, and it's a physical limitation in the sense that the wires either carry electricity or they don't, or well, they always carry electricity, but they have a low voltage or a high voltage, signifying either 0 or 1. Sometimes we talk about 0 and 1 as true and false. 1 is true and 0 is false. We often, not confused, but blend those 2 terms. But yes, but. Everything in a computer is stored in zeros and ones. So we need to learn how to manipulate zeros and ones. And you think it's trivial that only 2 digits are how it can be, but it's really difficult at first. But later on, it will come natural to you, and you'll see the whole world in terms of zeros and ones. A little like Neo did in that movie, The Matrix. It was released before you were born. Did anybody see that? Who's seen? Okay, everyone's seen The Matrix. Except that when everything turned green and he saw all those digits, they still want zeros and ones. They were like ASCII. It's crap. I mean, computers only have zeros and ones. So I don't know what was going on with that movie. These are my slides. I didn't make these slides. I stole them from Cedric and Wayne, the people who wrote the textbook. So they have funny stuff that I don't think is funny, but they put them here in any case. This is a T-shirt worn by some PhD computer scientists, I guess. That says 01001101, 01001111, 01001101. It's very funny, I guess. All it says is mom, M-O-M. And we know that because these numbers are binary, zeros and ones. They are numbers represented in base 2. And we can translate them to decimal, 77, 79, 77. And we have a table that everyone uses since the 60s that maps numbers to letters. So this is ASCII code for, these numbers are ASCII code for MOM. And there's also base 16 representation that's important to computer scientists for various reasons that we'll get to. But the first step is to learn how to do this binary base 2 representation. And in the future, in the near future, you should be able to look at these numbers and just see, oh yeah, 77, 79, 77. Yes, you'll be able to do it. One more slide before we get to that. Everything on the computer is binary. Everything is stored in binary in terms of the zeros and ones. So documents, pictures, books are stored, PDF files are all zeros and ones. The programs we write, even though we write characters, that's translated to the ASCII codes, that goes to zeros and ones, that's how it's stored. Pictures, music, all of that is just zeros and ones. And if you look at a 0-1 string, a binary string like that, 0111, 0101, you can interpret it in many ways. You can interpret it as a number, just a number, 117, or you can interpret it as a character, U, or you can think about it as something, indicate, let's say, some kind of frequency that's being played, a certain note that's being played, or it could be a color, like 45.7% gray. So if we just see a string of zeros and ones, we don't necessarily know what it means. The context is important. That's also true for the computer. It interprets the same string in different ways at different times. So even though you know what the string is, you may not know what it actually means. Okay, one more slide before we get to the... There are only 0, 1 types of people in the world. Those who understand binary and those who don't. The joke is that 0, 1 is 2 in binary. Whereas the idiots who don't know this would think there are 10 types of people. I don't think it's fun. 1, 0 is 2. 1, 2 is not binary. Is that what you... 0, 1 is 1. Duh. Come on, Daniel, you're the class is okay. Let's talk. Oh, what? Before. Let's learn how to do binary. So this is a little table that you must not memorize. It lists the numbers from 1, so from 0 to 15, and their binary equivalents. And the idea of the slide is to teach you how to convert numbers from binary to decimal. Base 2 to base 10, and the other way around. But firstly, what you should notice is, what you should learn is how to count in binary. So it's actually not that hard. I mean, we start off with lots of zeros, 1 0 meaning 0. And if you add 1, we increment the first digit. So that 0 becomes a 1. And then we want to add another 1 to that. But adding 1 to that 1 makes it overflow. So 1 and 1 is 0. Hang on. 0, and then the next position gets a 1. And now I try again. That's a 0, so I make it a 1. Now it's all 1, so I'm going to up it to 0, 1, 0, 0. Now that's a 0, so the next number will have a 1. And then there's a 1 there, so it becomes 1, 0. So this pattern, 0, 0, 0, 1, 1, 0, is the same as this pattern, 0, 0, 0, 1, 1, 0. So this counting in binary, incrementing a string of bits one by one, is a kind of first step to learning how to count. Then, at the bottom here, is the actual calculation we are going to do to convert a binary number to a decimal number. And here's a long binary number, but we're not going to use this. I'm going to do another example. And then at the top, it's the position of the number. So that's the least significant digit, just as in normal numbers. If I have 4,766,242 Rand, the 42 Rand, 2 Rand is not really very important. If I had to 2 Rand with one, I probably wouldn't buy it. I don't have that money. But bottom line is that the last number, last digit is the least important. So this digit is least important, it's digit 0, then number 1, 2, 3, 4, 5. And then there's supposedly a little explanation of how to do this. But I find it easier to first think about decimal. So let's go to my little thingamajig. And I know you're tired of hearing this, and I'm tired of saying it year after year to different classes. But the website is not ready, and that's all down to me. I've not been lazy or kind of been busy. I've been preparing for the course for a long time, but it's not ready. Once it is ready, though, which I promised kind of maybe to be on Monday, all these slides, notes that I write, and all the videos, and these other slides that I show will be on the web. All right. So now we have a little issue with lighting. But let's see if I can do that. Okay, right. It should be a little brighter. Oh man, the shadow is going to bum me. I'm not going to turn. Let's see if this works. Now it's more pronounced. And I don't want a torch next to the camera. Let's see if this works. Oh man. Oh, never mind. I'll fix this soon. I'll find some kind of solution. I'll have to bring a little lamp as well to class, and we'll just have to live with it for today. All right, so let's see. I want to teach you how to do binary. Today is the 2115, the 2nd, the 6th. This is RW114. I always write that because I have so many notes. Page 1. Okay, right. I make a lot of these notes. And it's not quite focused. I think if I press this little button, it should try to focus on its own. Okay, well, fine. Okay, good. Now, right, it's focusing. Now, let's say I write down a string of this. Don't fuck with me. Okay, never mind. Let's say I write down a string of digits. It's not a number yet. It's just a string of digits. I'm going to write down 7, 5, 2, 1. Okay. You think of that as a number. Okay, this is irritating, isn't it? I'll just do that. And I think if I click here, it'll focus. Let's hope it stays focused. You think of that as a number, and that's because it's so innate to think of it that way, but it's not necessarily a number. I mean, if you think of that as a PIN code, you don't really think of your PIN code as 7,521. You think of it as 7521. So how do we make that mapping to a real number? I mean, what's the value of this number? How do we interpret this? You probably learned this at school, primary school, perhaps even kindergarten, but we can write the value of this number by saying, okay, well, that's the 0 position, that's the 1 position, that's the 2 position, or the 3 position, or as you probably call it, the 1s, the 10s, the 100s, and the 1000s. Well, we can do the same thing here. We can say it's 7,000. So that's 7 times 10 to the 3 plus 5 times 10 to the 2 plus 2 times 10, that's fine, to the 1 plus 1 times 10 to the 0. And we know that is 7 times 1,000. Just going to write this out. I know it's boring. 5 times 100 plus 2 times 10 plus 1 times 1. And that's 7,000 plus 500 plus 20 plus 1. And that's equal to 7,521. So even though we don't think about this explicitly, this is what is going on when we are working with decimal numbers. And it's really quite complex. You have to add this stuff, multiply this stuff. And it's just because of your vast experience and expert knowledge about decimal numbers that you are so good at it and think about it as something just happens automatically. We can do exactly the same thing with binary. I'm going to pick a binary number, like it's just a random string, 101101. Just a random binary number I've just made up. And that's the 0 position, the 1 position, the 2 position, the 3 position, 4 position, the 5 position. So this number is equal to 1. I took the 7. So it's a 1 times 2, that's my new base, to the 5. It's not 10 to the 5, I'm now working in base 2, binary. Plus 0 times 10, oh fuck, I'm sorry, damn. 0 times 10 to the 4, plus 1 times 2 to the 3, plus 1 times 2 to the 2, plus 0 times 2 to the 1, plus 1 times 2 to the 0. And if I multiply that out, okay, now, next thing, perhaps even more important. The powers of 2 play such an important role in computer science that you must learn them. You must learn the powers of 2. You don't have to do this explicitly, It will come naturally. Don't be afraid when it happens. It's just part of the natural process. So when I wake you up in your bed by the end of this course, you must be able to tell me the powers of 2 are 1, 2, 4, 8, 16, 32, 64, 1, 2, 8, 2, 5, 6, 5, 1, 2, 1, 2, 4, 2, 4, 8, 4, 0, 9, 6, 8, 1, 9, 3, and so on. We must learn that, which is why I know instantly that this is 1 times 32 plus 0 times 16 plus 1 times 8 plus 1 times 4 plus 0 times 2 plus 1 times 1. So 32 plus, that's a 0, that's, oh, I'll write it, that's an 8, that's a 4, that's a 0, that's a 1. Now I can't do addition. I can't do addition. Let's see what's going on. The 8 and the 32 is 40, 44, 45. Okay. So this string here is equal to 45. And that's how we go from binary to decimal. And how do we go the other way around? Not difficult, easy peasy. I'll just keep that. The other way around. It's 2015, it's the second month, 6, 9, 1, 2, 4. Okay, let's do the same thing first in decimal. I have a number in mind, which happens to be 1386, and I want to write it down in decimal. How on earth do I know how to do that? Well, the way I do it is I'd say, okay, how many thousands are in this number? Okay, there's only the 1, so it's 1 times 1,000 plus, and then that number minus this 1,000 is 386. So how many hundreds in 386? Well, 3. So it's that plus 86. How many tens in 86? 8 times 10 plus 6. How many ones in 6? Well, 1. So I'll just cheat and I'll just write that. Okay, so you get the idea. And then I can say, oh, well, the 0th position is 6. The 1st position is 8. The 2nd position is 3. What? And it looks stupid when you do it in base 10. But if we do this in binary, I'm going to do exactly the same thing. Let's pick a number. Let's pick the same number. No, let's pick a smaller number. Now, I'm not working with thousands. I'm working with the powers of 2. Those are my positions. So I need to know the powers of 2. Immediately, we have a need for the powers of 2. So let's see. There's 1, 2, 4, 8, 16, 32, 64, 1, 2, 8, 2, 5, 6, 5, 1, 2, and that's 2 to the 0. Two to the 1, 2, 3, 4, 5, 6, 7, 8, 9. I want to convert this number to the binary representation. So I'm going to start by asking myself, just as I did before, except my bases are different, how many 512s in 386? Well, none. Okay, that's fine. How many 256s in 386? Well, probably the 1. So this is equal to 1 times 256 plus, and now what's left over to convert? It's 386 minus 256, which is 130. Okay, that's fine. 1 times 256 plus. Okay, next lower power is 128. How many 128s in 130? This is a stupid number. but we know it's 1. And what's left is 2. And so you can go down, no 64s more, 2, no 32s, no 16s, no 8s, no 4s, only the 1, 2. So that's 1 times 2, 5, 6 plus 1. 2 plus 0.
You lost just by times 1.
What?
You got the second line here, you got the 2 left over, I just do it times 1 again there.
I want to write a digit times power position. So adding a times 1 here would have spoiled my pattern. Okay. Are you the person who didn't indent yesterday? Okay. Good, excellent. You indent. Someone didn't follow my instructions yesterday, indented programs properly. I will hunt you down. I will kill you in your sleep. You are all going to indent properly this year. Otherwise, I will be in jail probably by the end of it. Almost definitely. Okay, let's see. So this is 1 times 2 to the 8 plus 1 times 2 to the 7 plus 1 times 2 to the 1. And all the other positions are 0. So I can write it down. Position 0 Position 0 is a 0. Position 1 has a 1 digit. All the others are 0 up to 7, and that's a 1, and that's a 1. It's really important to understand how this works. You will be doing it at some point, often. In fact, this will be in a test, but apart from that, you'll be using it in your actual work when you write programs. But I'll be honest, it's almost never necessary to convert a big number like 386 to binary. And even if you're forced to at gunpoint or somehow, you will use a calculator. But often it's nice to quickly convert a small number to binary. So 96 or 48 or something like that. And it's important to know how the process works. Okay. So this is conversion from decimal to binary and binary to decimal. And once we understand this, we can convert any number in any base to any other number in any other base. I'm sure your teachers taught you that at school as well. But because we never use other bases at school, we're not familiar with it. But let's try, yes.
Calculate what you convert to binary, don't you have to specify demonstration 2?
Well. Happy? It's tedious to always write that, and most of the time we don't. Especially when you're typing, it's in an email or something, it's tedious to write subscript to. I think most of the time the context is clear, and I will almost never write a little 2 there. But you're right, somebody could have mistaken this for 11 million and 10.
Yeah.
So. 110 million and 10, yes. All right. Let's just do one thing for fun. Let's just try a fun thing. Let's try using your new knowledge to convert 666 base 10 to binary. No calculators allowed in this test. No cell phones, no talking, no shooting. Test conditions. To help you out, I'll write down the powers of 2. 2 to the 0 is 1, 2 to the 1 is 2, 2 to the 2 is 4, 2 to the 3 is 8, 2 to the 4 is 16, 2 to the 5 is 32, 2 to the 6 is 64, 2 to the 7 is 128, 2 to the 8 is 256, 2 to the 9 is 512, 2 to the 10 is 10. Okay. Done? Wow, that was fast. You've seen binary before. Wow. Let's just find the second version. That is you disqualified. Oh, the second version. You've done binary version. Hang on. The third version. Let's go for the third version. Okay. Oh, there we go. Right. What's your name? Tenor. Oh, what a English name. You're Afrikaans. What did you get, Clement?
I got 1010011.
Let's read that in groups of 4. Actually, no. Let's do it in groups of 3. 101 001 101 Ugly duckly. Let's see if Clement is correct. No, let's give everyone a chance to finish. We have time. We don't have time. Oh, damn. I'm so far behind. Okay, I'm quickly going to check it out. So that's a 0, that's a 2, that's a 4, that's an 8, that's a 16, that's a 0 and a 0. That is a 1 to 8, and that is a 5, 1, 12. So let's add it all up. 6, 4, 0, plus 24, plus 2. You add that up, you get 6, 6, 6. It seems Clement is correct-ish. Now you can't see. Right here. So, not very exciting in binary. There may be a faster way, but I'm saying the number is not very exciting. I mean, 666 sounds ominous. 101, 001, 1010, it's not, doesn't have the same ring to it. Okay. So, listen, I'm behind. We're not going to finish. I'm going to go back to the slides and just rush through them because I really want you to see some of them. So, let's do that. Okay. Right. So, this is basically the same thing we did just now. This tells us how to convert from decimal to binary using exactly the same idea. It's just more boringly put on the slide. I just did it more excitingly and clearly. Base 2 is really important for computer science, but there is another base that is just as important. Base 16, hexadecimal. Base 16 is really important because if we group a binary number in digits of 4, we nicely get 16 different digits. And we call those digits 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, A, B, C, D, E, F. So we often write numbers in base 16. It's much shorter than binary, and it's very easy to go from hexadecimal to binary and back. All you do is you group in groups of 4, and then you look up in this little table or from memory. So if we have a number like this, 1100, well, the first one is an 8, the second one is a 4, so that's 12, and 12 in hexadecimal is a C. It's a C digit. So 15 digits in hex, as it's often called, incorrectly. And we often use this. So we can write this big binary number that we had before, 6375 in base 10, or this long string in binary, we can just quickly convert to hexadecimal by grouping in these 4 digits and looking at the corresponding digit. We know that 6,375 is equal to 18E7 in hexadecimal. And if you want to be clear, you add the base. So that's hexadecimal, also very important in computer science. I'll come back to it if we have time. How do we add two binary numbers? It's important we do it a lot. It's just exactly the same as adding two numbers in decimal. You just add the digits, but if the overflow, if it's more than 2, you take a carry. In the same way that if you add two decimal numbers, if you add the digits 9 and 6, that gives you 15, but that's more than 10. That's 10 or more. So you only write down the 5 and the 1 you carry. 9 plus 6 is 15, so we write down the 5 and we carry the 1. And the same thing happens in binary. 1 plus 0 is 1, 0 plus 0 is 0, 1 plus 1 is 2, but that's our base, it's an overflow. So we just write down the 0 and we carry the 1. Now we have 1, 1, 1, that's 3, that's more than 2, 2 or more. So we write down the 1 and we carry 1. 1 plus 0 plus 1 is 2, so we write down 0 and we carry the 1. You should be carrying the 1 plus 0 plus 0 is 1, 0 plus 1 is 1, 0 plus 0 is 0. So the same thing happens on this slide. We had 3 plus 2 is 5, 1 plus 9 is 10, so we write down the 0 and we carry 1. 1 plus 0 plus 0 is 1. So you already know how to do that really. What happens if we have negative numbers? How do we subtract in binary? Well, the easiest way is to simply, instead of subtracting directly, we convert the bottom number to kind of positive representation, and then we add it. So the question is, how do we represent negative numbers? Well, how do we represent negative numbers in decimal? You just add a minus to the front. But in binary, we don't usually do that. We have a special way of writing decimal numbers, negative numbers. So, we want something from negative numbers. We want them to have a certain property. We want them to be so that x is a positive integer and integer, and we have the representation of minus x. When we add these two together, we want 0. X plus minus x is 0. So we want this property of our representation of negative numbers. This representation only makes sense if we have a limited number of bits. And that's almost always the case. Often when you work in the computer, you're talking about 8 bits at a time, 16 bits at a time, or 32 bits at a time. So we always limit ourselves to a certain number of bits. And in this example, there are only 8 bits. So this is going to be an 8-bit representation of negative numbers. But up at the top it says, assume all words are 16 bits. It works exactly the same way. The principle is the same, but minus 5 in 16 bits is not the same as minus 5 in 8 bits. Kind of. Right. So, we are looking for a number that we can add to this number, which is 11011. I don't know what this is. That's a 4, that's a 8, that's a 16, that's a 32. 32 and 16 is 48, plus 4 is 52. So that's plus 52. We are looking for minus 52. How are we going to represent it? So that if we add it up, we get 0. Well, one starting point is to simply flip the bits. But if we do that, we simply make all the zeros 1s and all the 1s 0. If we flip the bits of this 52 number, and we add them up, we'll have 0 plus 1 is 1, 0 plus 1 is 1, 1 plus 0 is 1, 0 plus 1 is 1, 1 plus 0 is 1, all 1s at the bottom. No carries. We want to get to 0, so we add 1 more to this number. 1 plus 1 is 0, carry 1, 1 plus 1 is 0, carry 1, 1 plus 1 is 0, carry 1. Add one more, and then we get to 0, 0, 0, all zeros. So the formula for finding the negative representation of a number in a limited number of bits is flip all the bits and add 1. And this works if you go from positive to negative and from negative to positive. Works both ways. So, how do you compute minus x from x? You start with x, and here is the leading bit. It happens to be a 0, which is to us an indication that it's a positive number. We flip all the bits, so plus 4 turned into minus 5, and we add 1, get minus 4. It's a simple formula. It's a simple scheme, and it has a name. It's called 2's complement. Called 2's complement. So, if we have 16 bits available, what we've now done is to divide the numbers into 3 groups. Right here in the middle of the line is 0. 0 is in a group of its own. All zeros. If we add 1, we go to the positive side. So all the numbers above 0 are positive. And they all have the 0 bit as the most significant digit. Very first digit is always 0, meaning it's a positive number for 16 bits. Below 0, we go to the third group, which are the negative numbers. So minus 1 is all 1s. Minus 2 is all 1s except for the last digit, 0. And all the way down to this, which is the largest negative number I can store in 16 bits, if I'm using this scheme. There are other schemes, but they're almost never used anymore. So this is what you should know. We're either going to use this scheme with leading bit 1 meaning negative, all zeros, and leading bit 0 meaning positive, or we are only going to stick to positive numbers, no negatives whatsoever. And then this will be 0, this will be 1, that top number will be 32,767. And then if we add 1, we'll get this number, which will be 32,768 positive. And then we add up until we get to this number, which is no longer minus 1, but something like 65,556. So if you're using all positive numbers, then these negatives are all kind of positive. Yes?
So I don't understand why having a 1 there, which is like it's a 16 to the power 16, makes it a negative.
Okay, so
Like if you got that code, how it's a negative?
well, it's the way we divided all the possible numbers. We said that 0 is 0. If it's got a 0 as the first digit, it's a positive number. If it's got a 1 as the first digit, it's negative. So by looking at this number, I know immediately if we're using 2's complement, this is a negative number.
It's 11 to 16.
Yes. 2's complement is always relative to how many bits there are. So that's too big, but if we take a smaller number, are you telling me the focus is off again? That's not focused. Oh man. I'll put something there. All right, there we go. Focus on my finger. Yes. Oh, excellent. Good. So let's take a smaller set of numbers. Let's take 4 digits. But I'm working in binary. I'm working in base 2. So these are binary digits. And for short, we call them bits. That's where the word bits come from. So we're using a 4-bit representation of numbers. If you just flash a number in front of me and it's 100, 1000, 1 and 3 zeros, I know immediately that it's negative because it starts with a 1 and we're working with 4 bits. So this is really context sensitive. You have to know that we're working with 4 bits. But if I look at that, I know immediately it's negative because it starts with 1. So it's negative something, but negative what? Well, I can use the 2's complement rule to find out what it is. I flip the bits, 0, 1, 1, 1, and I add 1. Ooh, now I'm back to 1, 0, 0, 0, 0. But if I just interpret this as a positive 4-bit number, I'll know that this is 8. Although I'm cheating here. So that must be minus 8. Let's just take another example. If you show me 0, 1, 0, 1, 0, and you ask me what's the value of that, in 2's complement, 4 bits, I'll flip the bits, 0, 1, 0, 1. I'll add 1. 1 plus 1 is 0, carry the 1. 1 plus 0 is 1. 1 plus 0 is 1. 0 plus 0 is 0. And that's equal to, well, that's the 1's position. 2 plus 4, that's 6. So that must be equal to minus 6. Carry what is it?
0 plus 1 is 1.
Then I can say 0 plus 1, so no, forget about that. 1 plus 1 is 0, so we carry the 1. So I'm sorry, it's so natural to me, I cannot think like your primitive minds anymore. But 1 plus 1 is 2, you're right. Of course 1 plus 1 is 2. But 2 is our base, so that means I'm going to carry 1, and what will remain is 0. 1 plus 1 is 2, so I write 0, carry 1. 1 carry, plus 0 is 1. 1 plus 0 is 1, 0 plus 0 is 0. So that's right. Yeah, I'm sorry. This is confusing. Almost right on the screen. That's confusing, but that's really what I want to do. Okie dokie. Right. With 4 bits, it's actually much easier to represent the number line, the one we saw before as a table. So with 4 bits, I can show you that if I'm using positive numbers with 4 bits, this is my 0 point, and it's 0, 0, 0, 0. That's 1. 0, 0, 0, 1. And we go all the way up to 1, 1, 1, 1, which is 15. If I'm working with positive numbers only. Okay? If I'm working with positive numbers only, this is my number line. It goes from 0 to 15. If I'm working with 2's complement with 4 bits, my number line will go start at 0, which will be 0, 0, 0, 0. This number will be plus 1, which is 0, 0, 0, 1. This number will be negative 1, which is always 1, 1, 1, 1. That's minus 1. This side will go up to 7, which is 0, 1, 1, 1. This side will go down to minus 8, which is 1. So just to confirm, minus 8, I got that before. And this minus 6 will be right here. Okay. I'm out of time. No, I've got a minute. Just give me a minute. You can spare a minute, can't you? These bounds, you have to know how to calculate them. Let's say I tell you that you're going to use 9 bits. What's the biggest positive number you can represent using only positive numbers in 9 bits? Well, there's a formula. So positive, 9 bits. The minimum number is 0. The maximum is 2 to the 9 minus 1. 511. That is equal to 2 to the 4 bits minus 1, which is 15. So I can, if you tell me how many bits you're using, I can immediately tell you the largest number you can represent. If we are using 2's complement, 9 bits, the minimum is 2 to the 8 negative. And the maximum is 2 to the 8 minus 1, 2, 5, 1. So we have these formulas that tell us what are the numbers we can represent in a certain fixed number of bits. Okay, once again, I'm over time. I don't know what I'm going to do, but we'll have to stop. Thank you very much. And remember, if you were not able to log in yesterday, and you've not given up your number yet, please come in, okay? Or if you weren't there.